Okay, so let's see.
You need a person over here.
I'm going to be talking about Fourier series again, and the first topic is some mathematics, and I want to just tell you the results of various theorems rather than go through the proofs of the theorems. And then I'll go through a derivation of something that came to me as I did the examples. Namely, I found that if you had a function that had a certain degree of smoothness, then the Fourier coefficients had the nth Fourier coefficient went as 1 over n squared or n cubed and so forth. And it seemed to be happening, they seem to be more, the series seemed to be more convergent than one would think. And so I worked out the details of that. Whether knowing all about those details is all that important, I don't know, but I thought I'd just do it anyway. Yes?
I have two questions. But one can be enough.
One can, all right.
First question, for the integrals that is in the homeworks, do we have to do it, all of them by hand?
No. I think it's okay to use Mathematica or whatever you want, Python or something.
Okay.
To do those, or an integral table. And
Okay.
in fact, doing them by hand, what does that often mean? It means using an integral table sometimes, right?
Yeah.
Well, you might as well use an electric integral table. Mathematics, so.
And the second question is...
But, trust but verify with
Trust me.
Yeah, second question.
2.13
213.
is very vaguely...
I think this is totally spurious. Yes? Yes? Who's this?
One pages.
Oh, yes. Yes.
How are you?
I'm fine. Is something wrong? The dogs get loose or something?
No, I saw that example, but I still don't know how to do it exactly.
No, I don't know how to do it.
Yeah, I'm terribly busy. Can I call you back later?
Yeah, of course. This is my phone number. Call me whenever.
Okay, thank God.
Yeah,
Sorry about that.
213 is...
213, the problem.
Yes, it has... I think it refers to something in the page 100, the example that is at the end of page 100, but it's still slightly difficult to understand how the example...
Oh, no. Yeah, 213 is discussed in the book.
Yeah, but like, in a very short paragraph.
Well, I try not to, waste a person's time by going on and on. Everything you need to know about 213 is in that example. But I'll cover that today.
Okay.
I hope.
Okay, that's fine.
All right, so let's see where we were. So the question was, how does Fourier series converge? And first of all, what we mean, of course, is Fn of x is the sum k equals minus n to n. So this is looking at the series from a mathematical point of view, in which it's a finite series, and then we take the limit as n goes to infinity. This is f sub k EPI 2 pi kx over L, and then normalization factor. And then the formula for fk is integral 0 to L f of x e to the minus I 2 pi kx over L, normalization factor dx. Okay. Now, once again, the exponentials are clearly periodic with period L, So this Fourier series is certainly periodic with period L, whether or not the function f that we're trying to represent is periodic. And so in fact, what we wind up representing is not necessarily the function, but in general, it's the periodic extension of the function. And fp of x plus nl is simply defined as f of x for x in this interval, the interval being defined by what your integration region is, and integer n. So this is called the periodic extension. And I have to look up how to spell extension. I've never been a good speller. In fact, one of my favorite things about computers is that they correct my spelling sometimes. Unfortunately, sometimes they deform it and change a word into something I never meant to say. Okay, so that's the periodic extension. So the Fourier series represents not necessarily the function, but its periodic extension. Of course, they're the same if the function's periodic with that period, L. Now, a definition. A sequence of functions, Fn, of x, converges to a function f of x on a closed interval AB. Closed means that you mean the set of points between A and B, but including A and including B, including the endpoints. That's closed. And the surprising thing is that it makes a big difference when a function is defined on a closed interval or an open interval. The easy way to see that is consider the function f of x equal to 1 over x. This is well defined on the interval 0, 1 that's open, okay? But if you try to look at this function on the closed interval, or even on the half-open interval, you see this, it goes bananas at 0, okay? So the function f of x is equal to 1 over x is bounded. Well, no, it's not actually bounded even on the open interval, but it's certainly continuous on the open interval. But not on the closed interval, because it's not even defined at 0, really. And so that's the sense in which open intervals and closed intervals are really different. If you have a function that's continuous on a closed interval, it turns out to be bounded there. But if the interval's open, well, f of x is continuous on this open interval, but it sure as hell isn't bounded there because of its behavior as 1 over x at 0. Okay, so definition then, a series of functions converges to a function f of x on a closed interval if for every epsilon greater than 0, and each x in the interval there exists an integer. Mathematicians love to do that. There exists an integer n of epsilon and x such that, I'll just write that as st, such that the absolute value of f of x minus fn of x is less than epsilon for all n, well, capital N, greater than capital N of epsilon and x. So this is what I said before, and I guess I focused on closed intervals because of what I wanted to say later. I think one could use this definition for open intervals. It's the series converges on an open interval if for every epsilon and each x in the open interval is an n such that that's true. So I think that's generally true, an appropriate definition. But now where closure comes in is, suppose we can drop the, we can replace n of epsilon and x with simply n of epsilon. So then we would be saying that the absolute value of f of x minus fn of x is less than epsilon for all n greater than some n of epsilon. So this would have to be true on the whole interval. Then what you have is, then you have uniform convergence. And, okay, any questions? All right, so these are just definitions, really. The next definition is f of x is continuous. You probably learned these things 4 or 5 years ago. On an open interval, AB, if for all x between A and B, the two limits coincide, and the two limits are f minus 0, which is the limit 0 for positive epsilon so that, in other words, this is the limit of f of x from below. This is f of x minus 0. And f of x plus 0 is limit, again, epsilon is positive. So those are the two definitions. So for every point x, we can take the limit from below and the limit from above. The function is continuous if these two limits are the same. So it's continuous if f of x minus 0 equals f of x plus 0 for all x in the interval. If the interval is closed, then it's slightly different because what you need on the closed interval is you need it to be continuous on the open interval, and then you need f of a plus 0 to be f of a, and f of b minus 0 to be f of b. And so this is where the distinction between open and closed becomes really important when you have a continuous function that's not bounded on the interval. And, okay. All right, any questions? Now, here's a theorem that one usually proves in some sort of calculus class. You have a sequence of continuous functions. They converge uniformly on a closed interval. That is to say, AB closed. So we've defined what uniform continuity is on a closed interval, namely that the lower bound on n's such that you're less than epsilon is independent of the point x. So if you have a sequence that is convergent uniformly on a closed interval, then of course what you know is that f of n of x minus f of x is less than epsilon for n greater than n of epsilon without reference to x. And so then, by the way, since these are continuous on the closed interval, they're automatically integrable there. In fact, I skipped that line and then I inserted a new line into the text of the book, namely that if a function is continuous on a closed interval, maybe I should just write it down. If f of x is continuous on closed interval AB, the integral f of x dx from A to B exists, or is well defined. So continuous function on a closed interval is always integrable on a closed interval. One reason is that it's bounded on the interval. Yes?
What if it's continuous only on the open interval? Is the integral still defined or not?
Well, it depends. Suppose you wanted to do the integral from 0 to 1 of dx over x. It's continuous on the open interval, but this is infinity.
Okay. Yeah, I was actually thinking of the natural log example that's in the homework.
Yeah, it's a
That
natural
showing
log.
that
It's a
doesn't
natural
work.
log
So, yeah.
of 0, of 1, which is 0, minus a natural log of 0, which is minus infinity. And so that's basically it. When you've got open intervals, you need to worry a little bit. That's where the trust plus verify comes in. You verify. Of course, if you're using Mathematica, I think they've improved lately, but it used to be that you'd ask the program to integrate something, and it would ask you questions. I mean, is A real? Is it positive? Is it this or is it that? I don't know. Now it's better than that. It assumes the natural, it makes the natural assumptions and then gives you the answer under those conditions and then tells you all the assumptions it made, which is better. Okay, so let's see, where was I here? So a function that's continuous on a closed interval is integrable there. And now we're looking at, we're considering a sequence of functions that converges uniformly on a closed interval. Well, then the point is that we can take these integrals from A to B, fn of x dx minus ab f of x dx. Both of these exist, so we can subtract them, and the difference, of course, is less than or equal to, or let us put it this way, maybe I'll do this in 2 steps. This thing is equal then to the absolute value of fn of x minus f of x dx. And this is less than or equal to the integral from a to b of the absolute value of fn of x minus f of x dx. This thing goes to 0, and so this is less than epsilon times b minus a, because this difference here is less than epsilon as long as n is greater than n of epsilon. So the point is then that we can integrate term by term if we're dealing with a uniformly convergent sequence of continuous functions on a closed interval. So we have fab fn of x dx, this is equal to ab limit n to infinity Fn of x dx, and that's integral ab f of x dx. So that's yet another result or theorem. All right, the next thing is, once again, a definition. So let me use this blackboard space. Piecewise continuous. So a function is continuous, let us say f of x is piecewise continuous on, say, a closed interval AB, if it's continuous there apart from finite jumps at finite points x. So in other words, piecewise continuous is the sort of function, continuous is the sort of function you draw if you wrote with a pencil on a piece of paper and made a mark. If, on the other hand, you have some nervous tic, and you draw the function, and your hand bounces, or you draw the function, and there's an earthquake while you draw it. You're living in Chile a couple of days ago. Then in fact, that's called piecewise continuous. So, in other words, if the function looks like this, nice and smooth, and then there's a jump. And then maybe it goes down, another jump. So this function, I mean, assuming that this point, that for every x, the idea is for every x, we have a definite f of x. That's necessary for it to be a function. But then at certain x, f of x minus isn't the same as f of x plus. But that only happens at a finite number of isolated points, and the jumps are finite. Okay, that's piecewise continuous. And in fact, previously, when I said the periodic extension is actually, I'm going to use that phrase to mean that we not only extend it beyond the interval in a periodic manner, but also that we fix these jumps. How do we fix the jumps? Well, we don't quite fix the jump, but we sort of fix the jumps. We sort of fix the jumps by putting midpoints in there. So in other words, if there is a jump at, say, x equal to y, then we define f periodic at y to be a half f of y minus 0 plus f of y plus 0. So a half the limit of that plus the limit of that, and that would give you, okay, so in other words, you do the natural thing. The thing that you would do if somebody asked you, fix this, make this function nicer, and you do that. Because otherwise you'd say, well, and I mean, originally the function was defined so that f of x was either that, and then it jumped to there. So now what we're saying is that f of x is actually that, and for x less than y, it's doing this, and for greater than y, it's doing that. And so there's still a jump, but f periodic at y has a sensible definition. Okay, now I'm going to give you Fourier's Convergence Theorem, and I'm not going to prove it because this would probably, well, I don't know. I don't know how long it would take, half an hour, 2 weeks, anyway. But the Fourier Convergence Theorem, and the reference is Courant, page 439. This is a 2-volume treatise that I think, well, All right. Anyway, it's a 2-volume treatise that was written by Courant and Hilbert, if I remember correctly. And if you read some of it, it's a very, very nice treatment. You get the impression, at least I got the impression, that I was sitting in their living room and they were both on a couch, and I was in an easy chair. There was a fire in the fireplace, and it was, I don't know, 8 o'clock at night or something, and they were explaining their book to me. That's kind of the impression you get reading it. So it's very different from the sort of in-your-face lemma theorem proof approach of many mathematics books. It's a much more conversational thing. So I recommend it. On the other hand, there's a lot of stuff there. Okay, so their theorem is this: the Fourier series Fn of x for a function f of x. Now, what is f of x? It's piecewise continuous. So piecewise continuous with piecewise continuous first derivative. So in other words, we have f of x on an interval. It's piecewise continuous, and moreover, you can differentiate it, and when you do differentiate it, the derivative is almost continuous. That is to say, it's piecewise continuous. And the statement then is that the convergence to what? To the periodic extension of f. So notice, since it's piecewise continuous, it's not going to converge, the series isn't going to converge to f in general, it will converge to its periodic extension, including the mending at any jumps. So it converges to its, actually the thing is, right, it's piecewise continuous, so this is important that you mend any jumps. So the convergence is uniform on every closed interval. So it's uniform on every closed interval on which the function is continuous. And it's absolute if there aren't any discontinuities. Well, in fact, if it's continuous, there aren't any discontinuities. I'm a little puzzled what I meant by that. Anyway, so if the functions so there are two statements. The first statement is the Fourier series of a function that is piecewise continuous with a piecewise first derivative converges to its periodic extension. So that's a general statement. On the other hand, the convergence is uniform on intervals, or in fact subintervals, where it's continuous. All right. So, now let me say some things that are a little bit technical here. A function, the kth derivative of a function, I'm going to write this way, f parenthesis k. That means you're differentiating k times. If f of k is continuous, then f of x is in class ck. So ck means that they're functions that are continuous, that have k continuous derivatives. That's what ck means. And Okay, so let's think about something that is continuous, that is in class CK. So, and let's just, for definiteness, take this to be the interval. So these are the Fourier coefficients, and I'll write them without the 2 pi's to avoid, to just get rid of some of the clutter. And the question then is, if this function is in CK, what can we say about how these coefficients shrink as n gets bigger? And that has to do with how well the series converges. And so, I do have to remember to stand up. Great. So, now f, what I'm thinking of here is that f is not simply continuous, but I'm also thinking of it to be periodic. So, so now I'm going to say that f of x is in CK and f of x is periodic. Of course, with period 2 pi, because we're considering an interval length. Okay, so now let's do the usual integral by parts routine. We can certainly integrate the exponential. That's my favorite function to integrate. And then, actually my favorite one is e to the x. But this is almost as good. And we can differentiate f, and we can differentiate k times. So let's just differentiate one. Let's do one integration by parts. And in fact, I'm going to do the integration by parts the way in which we don't have to remember anything. We just use common sense. And the common sense is that d by dx of f of x times e to the minus I n x over minus I n minus f prime of x e to the minus I n x over minus I n. Okay. So here I've just taken this formula and written it in a very complicated way. When the derivative hits the f, we just get this term that cancels. When the derivative hits this, it just turns this ratio into e to the minus I n x. So this is the derivation of integration by parts for this special case. But now, we can do this integral, the first integral, because it's a total derivative. But on the other hand, both the phase factor and the function are assumed to be periodic. The phase factor is, you're assuming that f is periodic. So this thing, the surface term vanishes. And so Fn is just the integral minus pi to pi f prime of x, which exists since this is in CK. Thank you for moving the camera. E to the minus I n x over I n dx. So that happens when you integrate once. Okay. But you can do this k times because it's in CK. And each time the thing is, well, yeah, one of the curious things about periodicity is it's hereditary. If a function's periodic, then all its derivatives are periodic. And I suppose all its integrals are if you're careful about the limits.
Usually the argument for the surface term vanishing is you evaluate it at infinity.
Okay, give me that again slowly.
Usually the argument for the surface term vanishing is you evaluate it at infinity.
We're just on a closed interval. We're just minus pi to pi. The interval is minus pi to pi. We're into this.
So why does the interval dx
The integration is from minus pi to pi. The integral of the derivative of something is its it's f of pi e to the minus I n pi over minus I n minus f of minus pi e to the I n pi over minus I n. These two things are equal,
Okay.
and f is periodic, gets 0. Let me get you candy, though. Maybe I can get you water. Okay, here's the candy. Can you catch it? Good catch. Good. Okay, so Fn is that. If we do this k times, we get minus pi to pi fk, which exists, and in fact is continuous, e to the minus inx over in to the k. We call this the ink theorem. So what you see then is that the coefficients go down as n to the k. And one of the things, though, that one can notice by doing actual examples is that the coefficients tend to go down as n to the k plus 2, not n to the k. And so I asked myself, why is that the case? And let me just try not to take too much time explaining this. But let's just see. Well, first of all, what we've got so far is that because f is in ck and is periodic, okay, keep in mind f has to be periodic, then what about, so it has k continuous derivatives. What about the k plus first? Well, typically the k plus first will be piecewise continuous. In other words, you don't go from saint to sinner directly. You sort of become, I don't know, Republican and then sinner. There have been good Republicans. Eisenhower, Lincoln, maybe the first Teddy Roosevelt. Anyway, all right. So you go from having a continuous k derivative to maybe the k plus first one is, say, piecewise continuous. So this is typically the case. So if k plus 1 of x is piecewise continuous, then you can certainly integrate it, and you can even you can do this trick one more time, and what you find is that f of n is integral minus pi to pi, and now it's d by dx f k of x e to the minus nx over minus in to the k plus 1 minus f k plus 1 of x e to the minus inx over minus in to the k plus 1 dx. Okay, so that's what you get if you take this expression and you say, okay, or let us write this down, you differentiate, and the differentiation there gives you f of k plus 1, which is piecewise continuous, and then the derivative on this gives you that term, and the thing cancels in total. So we get this. This thing is still periodic, so that thing vanishes. And what we get then is minus pi to pi fk plus 1 of x e to the minus inx over in to the k plus 1 dx. Okay, and since this is piecewise continuous, it's integrable. And so that exists. And so what we get then is that if f is in ck, but its k plus first derivative is piecewise continuous, then the Fourier coefficients go down as n to the k plus 1. Well, it turns out you can turn the crank a little bit further, because what you can say is, in most examples, in most simple examples, this piecewise continuous k plus first derivative is itself actually piecewise continuously differentiable apart from discontinuities. And so what we've got is that f k plus 2 is something that is piecewise continuous plus jumps, plus a finite number of delta functions. Delta of x minus, what do I call it? X minus, oh, I don't know, xj. So it's got a finite number of spikes, but otherwise it's piecewise continuous. And so between the spikes, you can do the integral, and the delta functions, I'm assuming, typically they have finite coefficients. And so when you turn the crank one more time, what you get is Fn is equal to, once again, the periodicity means that the surface terms cancel. And so what you get is f of k plus 2 of x e to the minus I n x over I n to the k plus 2 dx. And you can separate this into the part that's piecewise continuous and the part that's delta functions. And so then this is a sum over the intervals, j equals 1 to j, xj to xj plus, xj plus 1. The piecewise continuous part, k plus 2 of x, e to the minus I n x over I n to the k plus 2. And then you get the delta function jumps, j equals 1 to big J. Jumps are finite, so it's delta fj k plus 1 e to the minus I n xj over I n to the k plus 2. So in general, it's 1 over n to the k plus 2. And what's left is continuous on some closed interval apart from the jumps, and so it's bounded. And so what we get then is absolute value of Fn less than or equal to 2 pi times the maximum of the thing divided by n to the k plus 2. So this turns out to be what's typically true for ck functions whose k plus first derivative is piecewise continuous and whose k plus second derivative is piecewise continuous apart from a finite number of finite delta functions. And so that means that in most examples that you run into, that you can actually do with MATLAB or Mathematica or your fingers or an integral table, you'll almost always have this to be true. And that's why the series converges so well. Yes?
Get you up to the last sum, you have an f sub j to the k plus 1, and then down on the bottom, the I n to the k plus 2.
Yeah.
On the delta function term.
Right. And yeah, so,
In your book, you have.
okay, so let's see, we're talking about,
I was just wondering if those are supposed to be k plus 1 and k plus 2 or both.
yeah, you may be right. It may be that this should be like k, that this one should be k plus 2. Of course, I'm not sure. I'd have to think about it, but it's one or the other.
Because the delta could imply a derivative anyway, so I'm not.
The jump, yeah, the jump is in fk plus 2, so I guess it should be called delta fk plus 2. Thanks. Let me get you a candy here.
In the book, it says k plus 2.
Oh, it does?
Yeah.
Oh, what do you know? All right, here, let me throw you this. Good catch. Okay, so let's see. Can I borrow somebody's pen? Okay, you.
It's just on
Here, it looks like it was folded that way, so you can. I'm sorry.
Thanks. All right, so let's see some examples. The first function is a C0 function. So this just means the function's continuous. And so I've made it 0 for minus pi less than or equal to x less than 0, x 0 less than or equal to x less than pi over 2, and pi minus x for pi over 2 less than or equal to x less than or equal to pi. Okay. And this is actually continuous, and if we do minus pi to pi, then the thing sits there until it gets to 0, then it starts to go up like this, and then it comes back down. And it looks like that. So this thing is continuous. On the other hand, if you differentiate it, its first derivative, well, it'll be 0, and then it'll be 1, and then it'll be minus 1. So the first derivative is piecewise continuous. And what are the Fourier coefficients? Well, Fn is minus pi to pi, Fx e to the minus Inx, dx, and I'm putting in the square root of 2 pi this time, and the answer is minus 1 to the n plus 1, pi to the n minus 1 squared over square root of 2 pi n squared. So you see, the answer is that it converges as k plus 2. It's in class 0, so it goes down as 1 over n to the k plus 2. Now let's consider a C1 function. In this case, I took f of x to be 1 plus cosine of 2x for absolute value of x less than or equal to pi over 2, and 0 for absolute value of x greater than or equal to pi over 2. And so let's see, I should sort of draw this. Cosine, when it's plus or minus pi over 2, it's cosine plus or minus pi, and those are both equal to minus 1, and so the thing is 0 there. So the thing looks like this. And then it's just 0 beyond that. On the other hand, so this is the function. If you compute its derivative f prime is minus 2 sine 2x. And once again, at plus or minus pi, sine of pi is 0. So it doesn't look like this. It actually looks like that. Right? Because the derivative is 0 there. So that's why it's in C1, because the first derivative is continuous. And it has a piecewise continuous second derivative. Its Fourier coefficients then fn integral minus pi over 2, well, in as much as it vanishes outside that, we don't need to screw around with that. So we get 1 plus cosine 2x even minus I n x dx over root 2 pi. And then this is 8 sine n pi over 2 divided by root 2 pi 4n minus n cubed. Once again, that's k plus 2. K is equal to 1, k plus 2 is 3. The next example has an intrinsic interest as opposed to just something I pulled out of my nose. In fact, there's a certain magic that is about to appear, maybe 5 minutes from now. So let us consider the Fourier series for cosine mu x. So f of x is cosine mu x. The coefficients, the function's even. We're doing the interval minus pi to pi for simplicity, so all the sine coefficients are 0. The thing is real. So we just get 8, we just have to do the cosine coefficients. Minus pi to pi, cos nx, cos mu x, dx over pi. Well, you use the formula for the product of two cosines, and you get 0 to pi. Well, I shifted the interval before. How did I get away with that? Let's shift the integral at the beginning. So let's just say that we start out from scratch with this integral. 0 to 0. Now I am really puzzled here. What did I do there?
That's because it's even function, so
Oh, I can double it. Yeah, okay. Right, okay, so let's just let's do a little trusting plus verifying. So that's what we start with. We then rewrite it as cosine of mu plus n x plus cosine mu minus n of x dx over pi, and as was pointed out, the thing is an even function, so we don't have to do the integral from minus pi to pi. We just go and include a factor of 2, which presumably is in this cosine formula. Well, the integrations are very easy. We just get 1 over pi sine mu plus n pi over mu plus n plus sine mu minus n pi over mu minus n, and altogether that is 2 over pi mu minus 1 to the n over mu squared minus n squared. And this is true whether mu is an integer or not, although when mu is an integer, well, when mu is an integer, I left out the sign of mu pi. So when mu is an integer, we have a 0 here, but there's a 0 up here, so the thing is well defined. And so this gives us a nice series for this thing. Cosine mu x is equal to 2 mu sine mu x over pi, and it's 1 over 2 mu squared minus cosine x mu squared minus 1 squared plus cosine 2x over mu squared minus 2 squared minus cosine 3x mu cubed minus 3 mu squared minus 3 squared plus minus blah, blah, blah. Okay. And it's continuous at plus or minus pi. So this is an interesting series, and it's a very nice series. And let me make an application of it. What you can do is you can set x equal to pi, divide by the sine of mu pi, replace mu with x, and then you wind up with a cotangent expansion. Cotangent of pi x as 2x over pi, 1 over 2x squared plus 1 over x squared minus 1 squared. And here we've canceled the signs, these alternating signs. Looks like that. And then if you bring this over to the other side, you get cotangent of pi x minus 1 over pi x equals minus 2x over pi, and then this series, 1 over 1 squared minus x squared plus 1 over 2 squared minus x squared plus. Okay. And now what you do is you say, well, let's pick 0 less than or equal to x, less than or equal to q, less than 1. Then the absolute value of this nth term is less than 2q over n squared minus q squared. So the series converges uniformly on 0 to x. We can integrate it term by term. I'm running out of blackboard space here. And so what we get is pi integral 0 to x cotangent of pi t minus 1 over pi t dt, and this integral is the log of sine pi x over pi x, and this is a sum n equals 1 to infinity integral 0 to x minus 2t dt over n squared minus t squared, and then this is a sum n equals 1 to infinity log 1 minus x squared over n squared. Now if we exponentiate both sides, in other words, this one and that one, you know I'm going to break my neck here with a skateboard and 2 electrical cords. We get sine pi x over pi x is exp of sum n equals 1 to infinity log 1 minus x squared over n squared. And, well, the exponential of a sum is the product of the exponentials. An exponential of a log is just the thing itself. And so this is a product from n equals 1 to infinity of 1 minus x squared over n squared. Okay, now that's the thing that I was promising you would be magic. It's just one of these totally bewildering formulas. I mean, the idea of an infinite product, infinite sum, I can sort of wrap my head around, but an infinite product just strikes me as being really mysterious. And I think these things are really related to path integrals. If you want, I think that's the last chapter in the book, or not the last chapter, but maybe chapter 16 or 19 or something. And in fact, this formula is used in that chapter. Anyway, that's and you can also derive a cosine formula. The cosine formula is cosine of pi x equals product n equals 1 to infinity 1 minus x squared over n minus a half squared. So that's just pretty remarkable. There are these various infinite product formulas, and I guess many of them were discovered in the 19th century, and it seems to me Weierstrass was one of the people who was particularly good at finding them. Anyway, I think these are kind of magical formulas. Okay, now we've been talking about functions that are in class CK and thinking about their Fourier series and thinking about functions that are at least piecewise continuous. Then we have a convergent Fourier series. But there's a much wider class of functions that are related to Fourier series, and this is these are the functions that are square integrable on some closed interval. And so let us say that the integral f of x, absolute value squared dx, a to b, suppose that this exists. And by the way, a French mathematician, I forget his name at the moment, but Lebesgue, that's his name, though I don't really know how to pronounce it. Americans say Lebesgue, and I never learned the French way of saying it. Anyway, he defined a rather cute way of understanding integrals. And in fact, this is, by the way, very well described by Fourier and Hilbert. So if you grab one of their books, I think volume 1, you look in the index, Lebesgue integration, you can find a very nice description. It's only about half a page. Anyway, so if a function is square integrable in, let us say, this more general Lebesgue sense, or you could say the standard definition is the Stieltjes definition, which you learned in calculus class, and that implies Lebesgue. Anyway, if a function is square integrable on a closed interval a to b, then its n-term Fourier series will converge in the mean. That is to say, the limit big N goes to infinity, integral a to b, dx, f of x minus f sub n of x, alpha value squared. This limit is 0. So in that sense, you have a convergent series. And when you consider Fourier transforms as opposed to Fourier series, you have a very nice result. Namely, if a function is square integrable, then so is its Fourier transform. The Fourier transform exists, is square integrable, and the Fourier transform constitutes a one-to-one map between the space of functions and the space of Fourier transforms. And this is one of the things that makes quantum mechanics possible. If mathematics were broken, quantum mechanics was broken. So now there are two very simple observations. what happens if you integrate a Fourier series, what happens if you differentiate a Fourier series. And the basic idea is if you integrate, what are you doing? You're basically taking an average of the integral of a function over an interval, which is the length of the interval times the average of the function. So you're basically averaging. And when you average, you're making things smoother. When things are smoother, they have a better Fourier series. So when you integrate, your Fourier series becomes better. And we can see this explicitly because we can say, suppose f of x is some Fourier series, fn e to the I, for some reason, shows a stretched interval, then integrating once, we integrate a to b, dx prime, f of x prime. I don't know why I made that a prime, but anyway, oh, it's the integral up to x, that's why I made it a prime, it's not a to b. When you do that, you simply get f of 0 over square root of L, x minus a, minus I root L over 2 pi, sum n equals, of course, minus infinity plus infinity, fn over n e to the I 2 pi n x over L minus e to the I 2 pi n a over L. So you see you get an extra factor of 1 over n when you integrate. So this means the Fourier coefficients are smaller, the thing converges better. On the other hand, if you differentiate, it's exactly the opposite. You take the derivative and pull down an n. So the coefficients go up with n. And that's just part of this general rule that differentiation, it's easier, but it makes things worse. Integration, harder, makes things better. Okay. All right, the next topic is something about quantum mechanics. And I guess everybody's had some quantum mechanics, right? Please nod your head. You're an undergraduate, you haven't yet, or you haven't had any?
Besides modern physics, which doesn't really count.
Yeah, I really think that the undergraduate curriculum in the first year and a half, or maybe first 2 years, in most universities is a disaster for physics. It's like a frontal lobotomy. Frankly, I'd rather have a bottle in front of me than a frontal lobotomy. I don't know who invented that slowing. So, do you know? Anybody know?
Yogi Berra?
Who? Yogi Berra?
Just a guess.
No. Yogi Berra said some things that were amusing, somewhat accidentally, I think. But no, this guy was one of these very clever writers. Okay. All right, so listen, you who haven't yet had quantum mechanics, you're going to learn it now. But if you don't understand it, it doesn't matter. Okay. So I'm going to take a nice potential. V of x is 0 for 0 less than x less than L, and it's infinity otherwise. So we've got an interval in which the potential is 0, otherwise the potential is infinite. And what does that mean? That means that the particle has to be in this infinite square well. This is called an infinite square well. So potential looks like this. 0 L. So the particle's in here, classically and quantum mechanically. All right, the Hamiltonian, well, it's p squared over 2m plus the potential. Okay, so undergraduate, this is what you know as the...
I know that.
Yeah, right. Now, in quantum mechanics, here's the essential idea of quantum mechanics. The essential idea of quantum mechanics is that the momentum operator is associated with translations. translations in space. In other words, UPS, FedEx, that sort of thing. Okay. And in fact, the translation operator U of A is just e to the minus IPA over h bar. H bar is a small constant that you know about that sets the scale for when quantum mechanics can go. A is some distance, P is the momentum operator. This is a unitary operator because it's an imaginary exponential of a Hermitian operator. So this is a unitary operator. This implements translations in a space. It takes a state, shoves it. So this, I should have write this as UPS of A. And now, how do we do this if we're acting on a function? Well, if we're acting on a function, then UPS of A on, say, some function psi of x is going to be psi of x plus A. And so this should be e to the A d by dx on psi of x. Okay, because undergraduate, this generates the Taylor series. Okay, this is equal to psi of x plus a psi prime of x plus a squared over 2 psi double prime of x and so on. This generates the Taylor series. And so if we want these two to be true, then P has to be h bar over I d by dx. And that's basically that's where this comes from. It also means that P satisfies this commutation relation. XP, the commutator is I h bar. But the essential thing that's going on is that momentum is related to translations. We say momentum is the generator of translations. And that's the essence of quantum mechanics. Okay, so we can solve this. So this Hamiltonian then is minus h bar squared over 2m d2 dx squared plus v of x. And we want to solve the equation then minus h bar squared over 2m, say psi double prime means second derivative simply, equals e psi of x. Well, for x in this interval, this is the answer, and for x outside the interval, we have to add infinity over here. It's infinity minus h bar squared over 2m. So infinity times psi plus that times double prime is e psi. Well, there's no way of satisfying that, so we've just got to have the thing go to 0 at the endpoints. So the wave function psi of x, whatever it is, this eigenfunction of energy has to go to 0 at the endpoints. And if it does something like that, or it might do this, it's got to go to 0 at these endpoints. And all right, well, class is basically up. I think I'll just pick this up next time. I'm running out of space and time, so that's sort of covariant in some sense. Any questions? All right, let's end this.